Hello, my name is Yoochan from Seoul National University, and today I will present our talk, Exploiting Kernel Laces Through Taming Thread Interleaving. And this is the joint work with Professor Byoungyoung Lee and Professor Changwoo Min. We present our talk in roughly 3 steps. First, we briefly introduce the lace condition as a background, and then we classify the lace conditions into several types to explain which type of lace condition is unexploitable. Finally, we present our new method to transform such a lace condition exploitable. Let's start with the lace condition. The lace condition is a kind of bug that is persisted since the early days of multi-thread development, but only recently getting increasing attention from the security community. Taking some representative examples, Rudder was developed by academia in 2019 and found more than 30 lace bugs. And in the same year, Google developed their own kernel concurrency sanitizer and found more than 300 lace bugs. As a result, unlike other types of bugs, the number of lace condition bugs found by listed colors solely increased in 2019, maintaining its upward trend. So, what is the lace condition? Basically, lace condition occur when multiple processes access the same memory location, and it results in a different memory state depending on the access order. For example, suppose two instructions A and B are executed by core 1 and 2 respectively, and each of them read and write the same memory location. In this setting, we can think of two execution scenarios. One that the instruction A is executed before the instruction B, and the other is vice versa. If the former scenario produced the result X, while the latter scenario produced the result Y, we call this kind of situations the lace condition. The result can be the value stored in the memory or the value led by read instruction. But all lace conditions are not necessarily the vulnerabilities. In fact, such a situation casually happens in most of producer-consumer threading patterns. A lace condition is regarded as a vulnerability when it alters the control flow or the data flow and eventually results in a memory corruption. At this time, the lace condition consists of two or more pairs of lace instructions. When it comes to the vulnerabilities, they do not occur when the involved lace instructions are merely executed, but only when they are executed in a specific order. The problem is that we cannot always enforce such a desired order, as the multiple threads are scheduled in a non-deterministic fashion. In this sense, executing them in a specific order is pure luck, just like hitting the jackpot in a slot machine game. The good news is that computer programs never demand us to insert the coins to keep executing it. So we can try brute forcing it until we get the desired effect. This boils down to the question that whether such a desired order can even happen eventually. Specifically, even if a lace condition results in memory corruption that cause address leaks or RIP controlling, it cannot be exploitable even if we cannot enforce such a problematic execution order. One may think that this is not an important issue because brute forcing will somehow trigger the instructions in the desired order, but we will show that some lace conditions have the execution order that cannot be triggered by brute forcing. Now let's look at the types of lace condition vulnerabilities and their exploitability. We first classify the lace conditions by the number of variables that are involved in. Namely, if a lace instruction pair accesses a single variable or multivariable. The single variable lace condition is the most basic type of lace condition vulnerability, where every lace instruction pair centers around a single variable. For example, the figure shows two lace instructions between the instruction A and B and the instruction B and C. And they both interact with each other by a single variable. This type of lace condition vulnerability occurs when the instruction A, B, and C are executed in order. Specifically, the instruction B should be executed after the instruction A and before the instruction C. And we refer the time between them to the time window or lace window. The figure on the right describes a single variable lace condition vulnerability found in the Linux kernel. This vulnerability consists of two pairs of lace instructions, and both are accessing the same header inclusion variable. To see how this lace condition results in memory corruption, suppose the header inclusion variable is 1 when the instruction A is executed. You can see that this leaves the variable called RFB uninitialized. Now, if the instruction B is executed and write 0 to the header inclusion variable, the instruction C will then read 0 from the header inclusion variable, which results in the memory copy function calls with the uninitialized RFB variable. In this type, the lace condition is more likely to occur as the time window between the instruction A and C is larger, and it is less likely if the time window is thin. However, because there is an odd that such an execution order happens no matter how unlikely it is, brute forcing will eventually trigger the lace condition, allowing us to exploit the vulnerability. The other type of lace condition is multivariable lace condition, and it is more common in real world than the single variable lace condition. The multivariable lace condition may also consist of multiple pairs of lace instructions, but at this time, each pair accesses the different variables. For example, the figure shows two lace instruction pairs between instruction A and B and the instruction C and D, while the instruction A and B access the memory 1 and the instruction C and D access the memory 2. In this type, the memory corruption occurs when the instruction B and C are executed after the instruction A and before the instruction D. We have already seen that the time window between the instruction A and D that is supposed to contain the other instructions in core 2. But since there are two instructions in core 2, the instructions in it has its own time window. Let's call each time window X and Y respectively. We noted that when exploiting a multivariable race condition, the relationship between these two time windows is very important. So let's further classify the multivariable race conditions into the inclusive one and the non-inclusive one, according to whether the time window X contains the time window Y. If the time window X contains the time window Y, it is classified as an inclusive multivariable race condition. On the other hand, if the time window X does not contain the time window Y, it is classified as a non-inclusive multivariable race condition. Similar to the single variable race condition, the likelihood of triggering the inclusive multivariable race condition also depends on the size difference between the time window X and Y. As the size difference between two time windows is smaller, the race condition is less likely to occur. However, like a single variable race condition, brute forcing will eventually manage to trigger the race condition because there is an odd no matter how thin it is. However, this is not the case in the non-inclusive race condition. The example shows a non-inclusive multivariable race condition found in the Linux kernel. Basically, the kernel uses uninitialized memory if only the instruction B and C in core 2 is executed between the instruction A and D in core 1. However, notice that the instruction A and D locate back to back with each other without any branches, which suggests that the time window between them is very thin, 18 cycles to be specific. On the other hand, there is a huge time margin of 20 to 50 cycles between the instruction B and C. The instruction D will always be executed before the instruction C. In other words, it is simply impossible to trigger this vulnerability by brute forcing it unless core 1 stops the execution between the instruction A and D and extend the time window. Since this kind of vulnerability cannot be triggered by normal brute forcing, it's been difficult to find it through forcing. In fact, this kind of vulnerability has begun to be discovered only after forgers integrate the mechanism that arbitrarily stops the kernel execution. However, it is still impossible to trigger this type of vulnerability in real world because the attacker cannot control the execution of kernel when exploiting it. Therefore, most of these vulnerabilities are ways to exploit. However, there are a handful of methods to resolve this problem under certain circumstances. The first method is using the different core latency. There are CPUs that have cores with different frequencies, such as Qualcomm Snapdragon 845. It has two sets of cores, and each set contains four 2.5 GHz cores and four 1.6 GHz cores respectively. If you place the thread whose time window needs to be extended on a slow core and place the other thread on a fast core, you can reduce the difference between the time window and the instruction can be executed in order. However, this method is only possible if the target systems use such as CPU with different core frequencies. Also, to the best of our knowledge, since there are no CPUs with extremely different latency between cores, if the difference between the time window is large, it cannot applicable. The second method is using the thread scheduler of the kernel. For example, in the Linux kernel, where the config print option is enabled, context switching occurs even if it is operating in the kernel mode. Yanhon used this method and demonstrate how one can extend the lace window. Specifically, the set affinity function in the kernel prints the thread in another core and inject a thread to it. By injecting a thread between the time window X, one can postpone the execution of the instruction D, which results in the extended time window X. To visually demonstrate how it works, suppose the instruction A is executed first, then core 1 receives the request to reschedule from core 0. Upon receiving the request, core 1 changed the status of current thread to wait, and then it performed context switching to the thread requested by core 0. Meanwhile, the instruction B and C are executed in core 2. By the time the instruction B and C are executed in core 2, core 1 finished the thread that core 0 originally requested. It resumed the thread in the wait queue, hence executing the instruction D. However, this is only possible in kernels with the config print option enabled. But the Linux kernels use the config print voluntary option by default. In other words, this method does not work for most of Linux systems. As you can see, all previous methods have obvious limitations and are hardly useful in general. So what we need is a new method to extend the time window that can be used in general setting. To design such a method, we first think about how to extend the time window. It turns out that it all boils down to stopping the core while executing the instruction A and D, or degrading the performance of the core. However, the first method cannot be used because users cannot control the operation of the hardware, so we choose the second method, namely degrading the performance of the core. The key idea of exp lace is to keep lacing interrupts to indirectly alter kernel threads interleaving. We noted that the thread immediately executes the interrupt handler whenever it received an interrupt. This suggests that if the interrupt handling happens to fall into the time window we are targeting, the size of the time window will be extended while handling it. To demonstrate this idea, we found two types of interrupts that can affect the kernel mode execution: interprocessor interrupt and hardware interrupt. Let's call them IPI and IRQ in short. However, both IPI and IRQ cannot be directly sent from the user mode. They are only used in the kernel mode. Therefore, EXP-Lace attempts to indirectly send interrupts using system calls that internally transmit IPI and IRQ. The system call that send an IPI and the system call that send a request to the device, which eventually send an IRQ. So we found the system call that performs TLB shutdown internally transmit IPI. Since each CPU core has its own TLB, all TLB entries across different cores should be synchronized in multiprocessor systems. TLB shutdown is a process to synchronize the TLB of each core. For example, when unmapping the address or modifying the permission of the address in one core, first the core flushes its own TLB and find another course that may have the same address in the TLB and send an IPI to flush them. Finally, upon receiving the IPI, the core flushes the address through the IPI handler. To use TLB shutdown in extending the time window, an additional process is required to send IPI to the target core. In this figure, the process C is the one sending IPI, and the process A is the one that contains the time window we want to extend. The important thing here is that the process A and C must have the same memory map, and processes that shouldn't receive IPI must have different memory maps. If three processes have the same memory map, IPI is delivered to both core 1 and 2 at the same time, which results in extending both time windows. If the process A and C have the same memory map, and the process B has a different memory map, IPI is only delivered to core 1. So only the time window X will be extended. And the second method is hardware interrupt. Before sending interrupts, we need two steps. The first step is checking the core affinity of each IRQ. The core affinity of IRQ can be checked through the file shown in the figure. This file has a read permission for the non-privileged user, so attacker can find out the specific core. The second step is pinning the thread that has the time window needed to be extended to that core. If the process C calls the system call that sends a request to a device and IRQ is delivered in the middle of the time window X, the time window X is extended by inter-service routine, and we can execute the instructions in the desired order. Now let's look at the efficiency of EXP-Lace. We measure how many cycles are extended through EXP-Lace. As a result of measuring the extended cycle due to the IPI extend from 1.5 thousand to 20,000 cycles. The reason for wide range is that it can only flush one TLB at a time. When a large address is flushed, it takes longer because it is flushed several times. So the larger the amount of memory is being flushed, the longer the time window is extended. And hardware interrupts extend the time window by about 15,000 cycles. The reason for introducing IPI and IRQ together is that two interrupts can be used at the same time. IPI sends an interrupt to the core where a process with the same memory map is running, and the IRQ is sent to a specific core, so the conditions does not overlap. Using both methods at the same time, the target core is interrupted more often. This means the probability that an interrupt is transmitted while the time window X is running is increased. And if IRQ and IPI are received at the same time, the interrupt that comes first is handled first, and then another interrupt is handled. At this time, the time window is extended up to 200,000 cycles. Now let's exploit the non-inclusive multivariable lace condition vulnerability through EXP lace. Here is the non-inclusive lace condition vulnerability found in Linux kernel. The use-after-free vulnerability occurs if the instruction A is executed before instruction B, and the instruction C is executed before instruction D. But there are two problems in exploiting this vulnerability. The first is a non-inclusive lace condition, so no memory corruption would be triggered if an exploit only used normal brute forcing. The second is that there is no time to reallocate. To exploit a use-after-free vulnerability, a reallocate step must be required. However, this vulnerability cannot be reallocated because allocation and free must be done allocation step and free step and use step must be done almost simultaneously. EXP lace can solve two problems at once. According to our measurement, the time taken from the instruction B to reallocate is about, According to our measurement, the time taken from the instruction C to reallocate is about 3,000 cycles. As I mentioned earlier, the time window is extended at least 15,000 cycles due to EXP lace. So if the interrupt is received in correct timing, the vulnerability will modify the memory that should not be modified. Now we can user-friendly write to reallocate buffer. Since this presentation is not focused on memory corruption exploit technique, so I will explain it briefly. First, we spray the file structure pointer and we partially override data pointers and we partially override the data pointers in reallocate its relocated structure so that it leaves sprite area and lick the file pointer. And we use IOBC structures for arbitrary address read and arbitrary address write. So here is the demo. First, check the current ID and first bring the file structure and then create the process that send an interrupt and trigger the vulnerability and leak the file pointer and leak the correct pointer of current process. And finally, we trigger the vulnerability one more and override 0 to UID variable. Finally, we got the root permission. And in conclusion, there is a type of lace condition vulnerability that cannot be exploited with normal brute-forcing. And we introduced a new lace exploit technique, EXP lace. With EXP lace, which turn unexploitable lace into exploitable lace. We can exploit the unexploitable lace condition. EXPLIs utilize the hardware's basic interrupt mechanism, so it is not affected by kernel configuration or the specific hardware. So it is generally applicable. So it is generally applicable regardless of the kernel configuration or specific situation. Thank you. Yes, the question is there a white paper on this? Uh, we are writing, but not published now in uh, after. The next question is, I wonder for how many cases they try the technique in order to be sure it is indeed as far as it is to be. Uh, yes, we tested on Windows and macOS, and it practically worked. And we tested uh, more than 10 latent bugs for proof that the general technique. And then next is, are you planning to make the exploit public? Um, I think about that, but after working white paper published, I will publicly open the exploit.
Uh, Next question. Do you have GitHub or Twitter to follow for future release from you? I don't have a public GitHub ID enter, but follow uh, our lab site. I think it's our question. Was it difficult to find IRQ gadgets which are from Cisco's or West? No, yeah, it's probably the same mechanism. So it's it the yeah. Mm-hmm. Thank you for listening our presentation. Thank you.